Hello, welcome to lecture 4 of this course. In the last lecture, we discussed a generic two-level system. In this lecture, we are going to study a two-level atom interacting with a classical field, and this will enable us to introduce some theoretical tools, and also it will help us deepen our understanding about two-level atoms. So let us begin. Let us consider as an example of a real physical system a two-level atom interacting with a classical electromagnetic field, a laser. The atom is treated as a quantum system while the field is considered as classical. So we are considering that a laser field with frequency omega is incident on the atom, which is modeled as a two-level atom having the ground state is labeled as gate Z and the excited state is labeled as gate E. We assume that the laser field is monochromatic and its electric field is represented by this particular equation: E of t is equal to eta cap E0 cos omega t, where eta cap is the unit polarization vector of the electric field and E0 is the amplitude of the electric field. While writing this expression, we are not considering or we are neglecting the spatial dependence of the field, and we can do that if we assume that the wavelength of the field is much longer than the size of the atom. So we are assuming here that the wavelength of the laser is longer than the size of the atom, and this approximation is known as the long wavelength approximation. And sometimes it is also known as, actually more famously it is known as the dipole approximation. And under this approximation one can ignore the variation of the field over the extent of the atom, and this is a quite a valid approximation if one deals with optical transition, as atomic transition dimensions are in the angstrom scales while the optical wavelengths are hundreds of nanometers. Now we can write the electric field in this way as well. Say E of t is equal to eta cap E0 cos omega t. This we can write as eta cap E0 by 2 e to the power I omega t minus I omega t plus e to the power I omega t. So in fact, many times it is convenient to decompose the electric field into positive and negative frequency components, and we'll see the benefit later. So what I mean to say is that I can now write this as two parts. One is the positive frequency part and another one is the negative frequency part. By this I mean that this E plus of t is associated with e to the power minus I plus omega t, which is e to the power minus I omega t, this term. On the other hand, E minus t is related to e to the power minus I, this is negative frequency, minus omega t, so which is e to the power plus I omega t. The atom, which is modeled as a two-level system, has atomic transition frequency omega 0. So here say the ground state has energy 0, then the excited state will have energy h cross omega 0. The ground state, as I said, is labeled as gate Z and this is labeled as gate E. When the laser frequency, which has frequency omega,
when it exactly matches the transition frequency, when omega is equal to omega 0, we say that the laser is in resonance with the atom, or this is generally known as the resonant interaction. In general, the laser frequency is slightly detuned. It is slightly detuned or off from the atomic transition frequency, and this difference is quantified. So this is what our omega is, and this difference is quantified by a parameter known as the detuning parameter and defined as omega minus omega 0. We can write the Hamiltonian for the atom and the field as a sum of the pre-atomic Hamiltonian, so that is say HA, and the atom field Hamiltonian, let me write it as H of AF. In the basis state, Kg Ke, we can express the pre-atomic Hamiltonian HA in this way. Let me we already know how we can express an operator in the matrix form, so we can sandwich two identity operator this way. So we already discussed it in the first lecture. So now I have two states. It's a two-state problem. So therefore, if I open it up, I will have Kg Brazi HC Kg Brazi plus Kg Brazi HC Ke Brai plus Ke Brai HA Kg Brazi plus Ke Brai HA Ke Brai. So we'll have these four terms. Now we have this eigenvalue equation. When atomic Hamiltonian operates on the ground state, we are going to get the zero energy, and if the atomic operator operates on the excited state, it will pop out energy h cross omega 0, and this is what we will get. And also we know that these states are orthogonal to each other, so Kg Brazi, this scalar product is equal to 0. So therefore you can immediately see from these relations that the atomic Hamiltonian can be written as h cross omega 0 Kt Bra-E. Now what about the atom field interaction part of the Hamiltonian, that is HAF? What is this? The electric field interacts with the dipole moment of the atom, and this interaction is given by minus mu dot E, where mu is the dipole moment operator of the atom. While writing it, the electric field is considered as classical and the atom is considered as quantum. The dipole moment operator mu is equal to minus E R E for a single electron atom, with Re denoting the position operator of the electron. We can express the dipole moment operator also in the basis states of En, Ket E and Ket Z. This is our basis states, and it can be written in the matrix form as follows. Let me write it. We have the elements like Z, mu, Z, then we have Z, mu, E, E, mu, Z, and E, mu, E. In short notation, we can write this dipole moment operator in the matrix form as this term would be, first would be mu zz, this one, and then we have mu ze, mu ez, and mu ee. It can be shown that the diagonal elements of this matrix vanish as the dipole moment operator has odd parity. Let me explain. We can write mu zz in the integral form also. Mu zz is equal to z mu z, and in the Schrödinger representation, we can, in the integral form, we can write it as psi z star, and the dipole moment operator is minus ere psi z, and this is, the integration is taken over the full volume. Now the dipole moment operator, this has a odd parity, it's a odd function, but this wave function has a definite parity, and because of that, this overall, this whole integrand is an odd function, and because the integration is taken from minus infinity to plus infinity, so you know that integration over a odd function will result in 0. Okay, and that's the reason we have this dipole moment operator. We don't have the diagonal elements, and we'll have only the off diagonal elements mu ze and mu ez. Let me write the full form of the dipole moment operator as follows. We have mu is equal to kzz. You already know how to write it in the this Dirac notations. The full form, you know how to write it, so let me write it. And here I have kt bra e mu e e, then we have plus kz z mu e e plus kt e mu z z. So all the 4 elements I have written now, 4 terms. Now this term is mu zz, this term vanishes, similarly this term also vanishes, so therefore I can write it as z mu e, and this would be kz e plus e z. Let me define 2 operators. Atomic lowering operator sigma. So we are going from the excited state to the ground state. So this is the atomic lowering operator. Similarly, atomic raising operator would be, we are going from the ground state to the excited state. In terms of these operators, we can write the dipole moment operator mu as follows. We can write z mu e sigma plus sigma dagger. Let me write it sigma and sigma plus. The full Hamiltonian for the atom field system we can write in terms of these new operators as follows. We have atomic part and the atom field interaction part. Now I can write atom part is h cross omega 0 e minus z mu e sigma plus sigma dagger dot e. Sometimes this we can write also as h cross omega 0 sigma dagger sigma minus, this would be written as it is, sigma plus sigma dagger dot e. Okay, let me quickly show you. Sigma plus sigma, sigma dagger sigma, would be sigma dagger is the atomic raising operator going from the ground state to the excited state, and sigma is the lowering operator going from the excited state to the ground state. You can always remember it this way, it is easy. Then you see that this is scalar product of the kz's, and that would be equal to 1. Then we'll be left out with this here, and this is exactly this one. So that's the reason I can write the full Hamiltonian exclusively in terms of these atomic raising and lowering operators. Okay, now just like the way we decompose the electric field into positive and negative frequency parts, we can also do the same for the dipole moment operator. If you recall, we earlier wrote the electric field as E plus and E minus, where the electric field, this is the positive frequency part of the electric field, and it has this time dependence e to the power minus I plus omega t, so that's why it is positive frequency part, and E minus is e to the power I omega t. Okay, now exactly in the same way, let us see if we can do that for the dipole moment operator. The dipole moment operator is z mu e sigma plus sigma dagger. This let me write as mu plus and mu minus. Here mu plus, the positive frequency part, is related to sigma operator, the atomic lowering operator. On the other hand, mu minus is associated with sigma dagger operator. Why the time dependency here is the positive frequency part, on the other hand here negative frequency part? The reason is that it can be actually shown that the expectation value of this atomic lowering operator has time dependence e to the power minus I plus omega 0 t. Omega 0 is the atomic transition frequency. Similarly, we can show that the sigma dagger has time dependence e to the power plus I omega 0 t. Actually, let me show this. To do that, let me first write the atomic lowering operator as this, and we can work out the time evolution of this lowering operator using the Heisenberg equation of motion. So that would be IS cross d sigma dt is equal to sigma, because this atomic, it is related to the atom, sigma operator is atom. So let me just deal with this atomic part of the Hamiltonian only. Then I have here sigma, this would be h cross omega 0 sigma dagger sigma, and this would be equal to h cross omega 0. As you can see, this would be sigma sigma dagger sigma. This commutation relation can be very easily worked out, and that would be equal to, in fact this whole relation can be worked out, and this will give you h cross omega 0 sigma. Okay, let me quickly show you how it can be worked out. Sigma sigma dagger, first let me work it out. Sigma sigma dagger would be, sigma is this one, atomic lowering operator, sigma dagger is e z, okay, and that would be minus, you will have here e z, and here you would have z e. Okay, so I hope you are getting it. This is your sigma, and this is your sigma dagger, and this is your sigma dagger, and this is your sigma, and you can immediately see that this is going to give me this, minus kt bra e, and then if I multiply this by sigma, okay, and sigma here is you're going from excited to lower, so this is what you will have. If you can now immediately see that this will simply give you z kz bra e, and this is nothing but the lowering operator, atomic lowering operator. So we have I h cross, if I take the expectation value, d sigma dt is equal to h cross omega 0 expectation value of sigma, and immediately you see that I have the equation d sigma dt is equal to minus I omega 0 sigma, and if you solve it, trivially you will get the time evolution of this atomic lowering operator would be the sigma 0 e to the power minus I omega 0 t. Okay, similarly you can show that sigma dagger t is equal to sigma dagger 0 e to the power plus I omega 0 t, and that's the reason we can decompose the atomic dipole moment operator into two parts like this. Okay, we can now open up the atom field Hamiltonian using this decomposition in terms of the electric field as well as the dipole moment operator. So we have atom field Hamiltonian as mu dot E, which I can now write as minus mu plus mu minus dot E plus E minus. If I take the dot product on both sides, I will get four terms, so that would be minus mu plus E plus minus mu plus dot E minus minus mu minus dot E plus minus mu minus dot E minus. Now let me again write that mu plus varies with time as e to the power minus I omega 0 t, mu plus varies as e to the power plus I omega 0 t, and E plus varies as e to the power minus I omega t, and E minus varies as e to the power plus I omega t. So you can see that we have this term as well as this term, these two terms. Okay, let me write here mu plus dot E plus or minus, these two terms varies as e to the power minus plus omega 0 t. Similarly, you will have mu plus dot E minus, that will vary as e to the power plus I, here it will be I, omega minus omega 0 t, or mu minus E plus, that combination will vary as e to the power minus I omega minus omega 0 t. So clearly there are these two terms varies very rapidly, they oscillates very rapidly. On the other hand, these two terms oscillates with frequency e to the power plus minus, it oscillates with frequency delta, that is the detuning parameter, and that means that there out of these four terms, two terms will oscillate very rapidly, and if we assume that omega minus omega 0, this is the modulus of this is much less than omega plus omega 0, we can discard all the highly oscillating terms. This is a very reasonable approximation, as the frequencies involved are generally in the optical domain. So if this condition is there, then we can discard all the highly oscillating terms, and this approximation is widely used, and this approximation is known as the rotating wave approximation, or famously in short it is called RWA. Okay, now under RWA, under the rotating wave approximation, we can therefore write the atom field interaction term as minus mu plus dot E minus mu minus dot E plus. So therefore we can write, if I put up the terms here, I will have minus Z mu E dot sigma dot, let me write it, sigma dot E 0 minus, I'm writing the first term here, E0 minus, that is the amplitude of the electric field, e to the power I omega t, and from this second term I will have minus Z mu E sigma dagger dot E0 plus e to the power minus I omega t. Now this electric field amplitude vector minus plus, let me write it explicitly, writing the polarization state direction as eta cap, then the magnitude of the amplitude is E0, it is minus plus, and using this I can write the atom field interaction term Hamiltonian as Z mu dot eta cap E0 minus sigma e to the power I omega t minus Z mu dot eta E0 plus sigma dagger e to the power minus I omega t. Let us define a quantity known as the Rabi frequency, and it's a very important parameter. It is defined as omega is equal to minus twice that of the matrix element Z eta cap dot mu E by H cross into E0 minus, which is equal to minus of the twice that of the matrix element Z eta cap dot mu E by H cross E0 plus. Now assume that E0, these amplitudes E0 and E0 plus and E0 minus are real, and take E0 plus is equal to E0 minus is equal to E0 by 2, then the Rabi frequency we can write as omega is equal to minus Z mu dot eta E by H cross E0. Now generally the phase of the dipole matrix element, phase of the dipole moment matrix element, that means this guy, is chosen so that Rabi frequency is always positive, omega is greater than 0. The Rabi frequency characterizes the strength of the atom field coupling, and in terms of Rabi frequency, our atom field interaction Hamiltonian will take this form. It would be h cross omega by 2 sigma e to the power I omega t plus sigma dagger e to the power minus I omega t. Now the atomic state of our two-level atom can be written as superposition of the ground state and the excited state with the corresponding coefficients, complex coefficients Cg and Ce. The time dependencies are contained in this coefficients Cg and Ce, and the time evolution is given by the Schrodinger equation, that is I h cross del psi del t is equal to h psi, where we have this as atomic part and the atom field interaction part. Now if I use this state and then using this Schrodinger equation, we can obtain a couple differential equation for these coefficients, and we'll have I s cross del Cg del t is equal to h cross omega by 2 Ce e to the power I omega t, and we'll have del Ce del t is equal to h cross omega 0 Ce plus h cross omega by 2 Cg e to the power minus I omega t, or we can simply write del Cg del t is equal to minus I omega by 2 e to the power I omega t, and del Ce del t is equal to minus I omega 0 Ce minus I omega by 2 Cg e to the power minus I omega t. These coupled equations, these coupled first order differential equations involve oscillating terms at optical frequencies. Many a times it is more convenient to transform into a co-rotating frame to get rid of this fast rotation or the explicit time dependence, and to do that let us make the transformation, make a transformation. Let us take say Ce tilde, we are making the transformation from say Cg Ce to Cg tilde and Ce tilde. They are defined as Ce tilde is equal to Ce e to the power I omega t, and Cg tilde, it remains the same with Cg. And if I do this transformation, I can rewrite my couple differential equation very trivially as del Cg del t is equal to minus I omega by 2 Ce tilde, and del Ce tilde del t is equal to I delta, this is the detuning parameter, Ce tilde minus I omega by 2 Cg. Let me remind you that delta you will find as omega minus omega 0, where is the detuning of the laser from the atomic resonance. And now in the transform frame, the Hamiltonian in the matrix form, it would take this form. You will have 0 h cross omega by 2 h cross omega by 2 minus h cross delta. As you can see, the time dependency is no longer there, or if I write it in terms of the basis states, I have minus h cross delta kate e bra e plus h cross omega by 2 sigma plus sigma dagger. What we have done in more sophisticated language is termed as unitary transformation. Okay, and I think I have already discussed about unitary transformation in lecture 1, but considering its significance, let me once again remind you about it. Suppose we have a unitary transformation that takes us from the state vector psi to a new state vector psi tilde via this transformation. Say psi tilde is equal to u is the unitary transformation, u psi. Now the question is, how does the Hamiltonian transform? That means when I am in the old state vector, its time evolution is given by this Schrodinger equation, I s cross del psi del t is equal to h psi, and when I go over to a new state vector psi tilde, the its evolution, time evolution, is again given by the Schrodinger equation, but now here this h is replaced by a new Hamiltonian h tilde. I want to know how this h tilde is related to the old Hamiltonian. That we can do easily. Let me show you how to do that, how to find that relation. So I have I h cross del psi tilde del t is equal to h tilde psi tilde. Let me now use this transformation. Del t, here I have u psi is equal to h tilde u psi. Okay, if I open up the left hand side of the equation, I have I s cross del u del t psi plus u I s cross u del psi del t is equal to h tilde u psi, who is, I can again write as I h cross del u del t. You see this one, I s cross del psi del t. Okay, let me write here, plus I can write it as h psi, and I will take psi to the other side, so I will have h, in fact I will have uh. Okay, and then let me write here it is psi and h tilde u psi. From here I can immediately get what is h tilde if I multiply these sides or operate this side from the right by u dagger, then I will have h tilde, and I will have I h cross del u del t u dagger plus u h u dagger. So therefore I have this transformation relation, that the new Hamiltonian is related to the old Hamiltonian by this relation, and this relation is actually worth remembering. So this is what we have. We can immediately apply it for our considered case. If we take the unitary transformation as e to the power I omega t, take it as I omega t ket e bra e, and apply it to our two-level system case here, then we can show that this Hamiltonian h tilde would indeed turn out to be 0 h cross omega by 2 h cross omega by 2 minus h cross delta. Okay, now let us discuss an interesting phenomena which is known as Rabi flopping. First, we consider the case of exact resonance when detuning is equal to 0. That means our laser frequency is exactly tuned to the atomic resonance frequency. So the laser frequency, laser that is incident, exactly matches the transition frequency of the atom. In this case, the coupled differential equation that we wrote for the coefficient will take this form. It would be del Cz del T is equal to minus I omega by 2 Ce tilde, and the other one would be del Ce tilde del T is equal to minus I omega by 2 Cz. Now we can easily obtain the uncoupled second order differential equation from here. It's easy to see that you will get delta 2 Cz delta T2 plus omega by 2 whole square Cz is equal to 0, and delta 2 Ce tilde delta T2 plus omega by 2 whole square Ce tilde is equal to 0. These equations are well known and they are frequently solved in many textbooks. However, let me write down the general solution here. The general solution for these couple equations, the general solutions, CZT would be equal to A, say sine omega by 2t plus B cos omega by 2t. Now let me find out these constants A and B. At time t is equal to 0, I can write Cz of 0 is equal to B. On the other hand, I can find out the other constant A from this equation, because Ce tilde at time t from this equation I can write it as 2I by omega del Cz del T, and therefore I will get 2I by omega A omega by 2 cos omega by 2 T minus omega by 2 B sine omega by 2 T. So immediately you will find that this constant A would be equal to minus I Ce tilde at time t is equal to 0, and therefore thus we can write that Cz of t is equal to Cz of 0 cos omega by 2t minus I Ce tilde sine omega by 2t, and Ce tilde at time t is equal to Ce tilde at times t is equal to 0 cos omega by 2t minus I Cz at time t is equal to 0 and sine omega by 2t. Now assume that at time t is equal to 0, the atom is in the ground state. So this coefficient Cz is equal to 1 at time t is equal to 0, and C tilde at time t is equal to 0 is 0, and therefore the general solution will simply become Czt is equal to cos omega by 2t, and Ce tilde at time t would be equal to minus I sine omega by 2t. The ground and the excited state populations are therefore will be given by the probabilities. So Pg of t is equal to mod of Cg square, which is equal to cos square omega by 2t. On the other hand, the population in the excited state would be given by Ce tilde mod square, and that would be sine square omega by 2t. In fact, I can write it cos square omega t as half of 1 plus cos omega t, and this one I can write as half of 1 minus cos omega t. Clearly, the population oscillates between the ground state and the excited states at angular frequency omega. This oscillation phenomena is referred to as Rabi flopping. We can discuss this phenomena by a pictorial diagram. If I plot the probability versus the Rabi frequency, let me plot omega t rather, then initially the atom is in the ground state, so it will go from the ground state and this ground state population will oscillate with the Rabi frequency omega. On the other hand, the excited state will also oscillate, and it will be like this. So this bold one solid curve represents the ground state probability Pg, and this dotted one corresponds to excited state population. So here this is 0, this is pi, and this is 2 pi, and so on. The period of oscillation is 2 pi by omega. Now you can see some interesting facts from this plot. Say if the field is turned on for a duration, if the laser field is turned on for a duration, say half of the time period of oscillation, that is the time period of oscillation, then the product omega into t by 2, this omega Rabi frequency into time product would be equal to pi. So I'm talking about this one. As you can see, this means that the atom which is initially in the ground state is promoted to the excited state. You see here it's now going to the excited state with 100% probability or unit probability. This is 1. On the other hand, say we have and this kind of pulse are actually called pi pulse. So when the Rabi frequency into time product is equal to pi, the laser pulse is known as pi pulse. On the other hand, if we have this product as say pi by 2, if your omega t is equal to pi by 2, in that case this will refer to this particular point pi by 2. Actually this is 0.5. I'm not drawing it appropriately, so this is the point here. So in this case we'll be able to create a state which should be the superposition of the ground state and the excited state. So we'll have a state which will be superposition of the ground state and the excited state. So this method can be used for state preparation, though it has lot of issues, but in principle this method is useful for state preparation. In the case of non-zero detuning, that is when delta is not equal to 0, non-zero detuning, that means the laser field is not in resonance with the atomic transition frequency, we need to solve the coupled equation del C Z del T is equal to minus I omega by 2 C E tilde. Delta C E tilde delta T is equal to I delta C E tilde minus I omega by 2 CZ. This can be solved, and if we solve it, then one can get the solution like this. Cz of t would be equal to e to the power I delta t by 2 Cz 0 cos omega tilde by 2. I will define what is omega tilde here. Minus I by omega tilde delta Cz at time 0 plus omega Ce tilde at time t is equal to 0 into sine omega tilde by 2t, and Ce tilde, this would be equal to e to the power I delta t by 2 Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta Ce tilde 0 cos omega tilde by 2t plus I by omega tilde delta C tilde 0 minus omega Cg 0 multiplied by sine omega tilde 2 by t. Here this omega tilde is the square root of omega square plus delta square, and this is known as the generalized Rabi frequency. It is called generalized Rabi frequency. Just like in the resonant case, if we assume that initially the atom is in the ground state, that means Cg at time t is equal to 0 is equal to 1, and C tilde at time t is equal to 0 is equal to 0, then our solution would be Cgt for the specific case would be e to the power I delta t by 2 cos omega tilde by 2 t minus I delta by omega tilde sine omega tilde by 2t, and Ce tilde t would be equal to e to the power I delta t by 2 minus I would be there, and omega by omega tilde sine omega tilde by 2t. So the excited state population would be Pe of t would be equal to Ce tilde mod square, and this would be omega square by omega tilde square sine square omega tilde by 2t. Thus we notice that the Rabi oscillations now occurs at the generalized Rabi frequency omega tilde, and omega tilde is greater than omega. So clearly the oscillation rate, this means that the oscillation rate increases as the detuning increases, because as detuning increases omega tilde increases. And for weak fields the Rabi frequency, not the generalized one, is much smaller than the magnitude of the detuning, and which implies that the generalized frequency omega tilde is nearly equal to the magnitude of the detuning. This is for the weak fields. And for strong fields, actually weak fields and strong fields are defined in term compared to with reference to the detuning parameter. That's the reason I am telling again and again that detuning parameter is extremely important, because this is one of the controllable parameter for us. And for strong fields, the magnitude of the detuning is much smaller than the Rabi frequency, not the generalized, the Rabi frequency. So in that case, the generalized Rabi frequency would be nearly equal to the Rabi frequency. Now in the delta is not equal to 0 case, non-zero resonance, non-resonant case, one can't have excited probability. This population in the excited state can never exactly go to 1. Let me better write it. P can never be equal to unity, because the amplitude reduces. In fact, this can be shown in this diagram here. Pe of t, if I plot versus omega t, in the case of resonant case, it will be able to, suppose the atom is in the ground state, so it is excited state would be 0 initially at time t is equal to 0. So we will have this kind of a plot for the resonant case. This dotted one is for delta is equal to 0. On the other hand, if delta is not equal to 0, we'll have a situation like this. Here you see the oscillation increases, but it is unable to touch p is equal to 1. And here it would be pi, this would be 2 pi, and so on. Rabi oscillation phenomena clearly indicates that these states, kth states, kg and ke, are not eigenstates of the Hamiltonian, which is called the dressed Hamiltonian in a way because it is dressed by the laser field. So clearly kg and kt are not the eigenstate of this Hamiltonian. In fact, eigenstate of Hamiltonians we can work out, and they would be different from kg and ke, and they are known as dress states. Eigenstates of H tilde are known as dress states. Dress states formalism of a two-level atom is a very powerful tool.
Let me stop for today. In the next class, we are going to discuss the dress state picture of two-level atoms, and we'll conclude our discussion regarding two-level atoms. Thank you.